is more about SLCs. What is projection operator? How did we write it? Pj, right? Pj, then R is equal to what? Is it PJR or is it PJ? PJ, cannot be PJR. ठीक है. What is PJ? Sum over what? R. That is why it cannot be Pj of R, because we are summing over R. Sum over R, then chi R. Should I write a J here or not? Yes. Did I write it as a subscript or a superscript? Okay. Chi J R multiplied by, doesn't matter, you know what I am talking about, right? R. What is R? A symmetry operation. Okay. So, in order to use a projection operator, what you do is you take whatever basis element it is, make the R operate on it and multiply it by the character corresponding to that same symmetry operation R, and you do this for each and every symmetry operation and sum over. Right. The thing to remember is that we are summing over all symmetry operations. Right. So, summing over all symmetry operations means that, suppose for C3V, what is it that we have? What are the symmetry operations? E, 2C3 and 3 sigma V. We should not forget the coefficients. Right. Not only should we not forget the coefficients, don't forget we are actually using R. So, what we get for C3 operation is going to be different from what we get for the C3 square operation, isn't it? C3 and C3 square. So, they are going to be different. Characters will be the same, but the effect of R is going to be different. So, please don't forget to use each and every symmetry operation. We are going to need that today. So, today what we will do is, we will just work out 3 or 4 more examples of SLCs. While doing so, we will learn a useful technique of descent in symmetry and use of group subgroup relations. Alright. So, let us get ahead with it. We are going to talk about SLCs. Lecture 18 you said? What did we discuss last day? Where did we stop? So, this is the disadvantage of not having slides. I also don't remember. C2H4 is all that we did, right? So, right now we are following Cotton's book, almost page by page. Today we will digress a little bit into Carter's book. Okay. So, what I am doing now is really solve problems that are there in Cotton's book. So, let us go to the next problem, something like PTCl4 2 minus. What is PTCl4 2 minus? Is it tetrahedral or is it square planar? It is square planar complex, right? So, this is what it would look like. I am not drawing the atoms, and you can figure out what I have drawn. This point is platinum, then you have chlorine, 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 right? What is the point group? Yeah? D4H, very good. It is a D4H point group. Okay. So, let me write down the symmetry operations of D4H. I hate the ugly lines I always draw. So, I tried to get my son's ruler today, but then he did not cooperate. So I got this. Right. So the symmetry operations are E. Is this large enough? Yeah. Large enough, right? Yes, sir, or no, sir? 2C4. What are the 2C4 operations? C4 and C4 cube. What about C4 square? C4 square is C2. This C2. So you know which C2 I am talking about. And before going further, maybe I will draw the axis. Let us say this is X, this is Y, and then Z will be pointing towards us. Right? Okay. C2. Next, what would we have? Do we have more C2s? Do we have more C2s? Where are the C2s? One along the bonds, that is one kind. How many of those C2s are there? 2. And 2 will be between the bonds. So, those along the bonds are called C2 dash. Those between the bonds are called C2 double dash. Okay. What else is there? Before going to sigma, is there a point of inversion? Yes. And then I think everybody can see the horizontal plane, right? XY plane is horizontal plane. It is sigma h. And what else is there? So here we differentiate between sigma v's and sigma d's. Right. These are the sigma v's, these are the sigma d's. The ones that go through the bonds are called sigma v, ones that go between the bonds are called sigma d. Okay? I will show you the character table. Okay, D4H, can you see? So E is 2C4, C2, 2C2 dash, 2C2 double dash, I 2S4, sigma H, 2 sigma V, 2 sigma D. Alright? And you, what was that? S4, we have forgotten S4. Now that's a mess. After drawing that line so carefully, I've forgotten. Where do I write 2S4 now? I'll write it somewhere here. 2S4. So don't get confused with the characters. Okay. Now, so right now we are focusing on sigma SLCs only. We are going to go on to pi SLCs today as well. Okay. I hope you have not forgotten what SLCs are. Do you know what SLCs are? Symmetry adapted linear combination. So it's basically a linear combination of wave functions or orbitals that are of a certain symmetry, right? And what we do using projection operators is that we try to project out these symmetry adapted linear combinations using the atomic orbitals as the basis. Okay, right. So the first step would be to name the orbitals. Let me call them. The problem is you cannot even see the color I use. Still, let me call them sigma 1, sigma 2, sigma 3 and sigma 4. There is no sigma 5. There are 4 sigma bonds, right? So these are basically the atomic orbitals, let us say s orbitals, that are being used by chlorine for the coordinate bonding or covalent bonding, whatever you want to call it. Do you see a difference in color between the line and the sigmas? I see it here, I don't see it there. Okay, no problem. So now the first thing to do is to construct the reducible representation using these 4 orbitals. Let's get ahead. The character of E is 4. What would be the character of C4? C4? everything will change places. 0. C2, C2 is the same axis, Z axis, 0. C2 dash, C2 dash, which 2? Not any 2, yes, any 2 that are in the same line going through the central metal ion, yeah. So 2, what was that? I am using the sigma 1, sigma 2, sigma 3, sigma 4. Let us say s orbitals of chlorine, we are using them as the basis and we are constructing the reducible representation. Okay, fine. C2 double dash, 0, we are all convinced, right? C2 double dash is 0 because this is where C2 double dash is. Sigma 1 goes to sigma 2, sigma 3 goes to sigma 4, right? So this is 0 and I have created enough space for writing the character of S4, which is 0. I 0. Sigma H 4, sigma V, where is sigma V? Here, right? It's 2. Sigma D 0. Very good. What is the next step? Next step is to break this down into the constituent irreducible representations. What is the relationship we use? Gamma equal to sum over J, Aj, gamma J, and every time I forget whether I wrote I or J the previous day, does not matter, right? And what is Aj? One by H sum over R chi R. If it is Aj, it has to be chi JR. Should not write chi IR. Okay. So now I will show you the character table. Please work out the Aj's. So what I get is gamma equal to A1G plus B1G plus EU. What do I do next? I have to use the PJ operators corresponding to A1G and B1G and EU on sigma 1. It does not matter, you can use any one, but conventionally we will start with sigma 1. So for that, what I need to do is, I need you to draw this diagram, because you need to know what is what, and then once again I will show you the character table and then you can work out, right. So what I want is, I want you to tell me what is P A1G operating on sigma 1, what do you get? What happens when you make P B1G operate on sigma 1? What do you get when you make P EU operate on sigma 1? Okay. So, ready for the character table? D3H, right? What is the point group? Point group? So, can you work out what happens when you make the projection operator of A1G operate on sigma 1? Okay, let us see. Let us work it out. You write, I speak. Okay. What happens when E operates on, see the chi R is very easy here, right? A1G chi R is all 1, right? So E operating on sigma 1, what do you get? Sigma 1 multiplied by 1, write that, plus C4 operating on sigma 1, what do you get? No, be careful now. C4 operating on sigma 1, what is it? One way it is sigma 4, the other way it is sigma 2. So you have to write sigma 2 plus sigma 4, isn't it? Plus minus. So you get sigma 2 plus sigma 4. There are two operations. Okay, what about C2? Sigma 3. So far what have you got? Sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Now, what is next? C2 dash. 2 C2 dash once again. What is C2 dash? The one going through the bonds, right? So, first C2 dash, what do you get? Sigma 1. Second C2 dash? Sigma 3. So, write sigma 1 plus sigma 3. So far I have 2 sigma 1 plus sigma 2 plus 2 sigma 3 plus sigma 4, isn't it? Then what about I? No, what about C2 double dash? Sigma 2 and sigma 4. So write plus sigma 2 plus sigma 4. It's very easy. It's like you're back to class 2, class 4 days. Okay. How far have we gone? 2 C2 double dash, right? Then I. What about I? You don't want I? Sigma 3. Then S4. Sigma 2 and sigma 4. Sigma H. Sigma 1. Sigma V, again there are 2 sigma V's. And 2 sigma D. So finally you get something multiplied by sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. But that 4 is not relevant, isn't it? The relevant part is and normalization is something that we can now do as a mental arithmetic. Sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. If it is to be normalized, what should be the coefficient? Multiplied by itself, what do you get? Suppose this is n, what do you get? Don't you get n square multiplied by 4 equal to 1? Why 1 by 2? N square, right? N square multiplied by 4 is equal to 1. So, n is 1 by 2, that's what you are saying. Okay. I thought you are saying equal to 1 by 2. Okay, fine. It's equal to 1 by 2. That was easy. Next is B1G. In B1G, we have to be careful because signs will also change, isn't it? Because all characters are not plus 1. Don't forget, it is a character multiplied by symmetry operation. B1G, first one is 1, second one is minus 1. So again, so from here we get sigma 1, then from here we get minus sigma 2 minus sigma 4, right? If there is a question, please ask. This is simple, but it is also very easy to get confused. Anup, then C2 sigma 3 plus sigma 3, then C2 dash right. I hope you are writing. Then there is a minus 1 and the operation is 2 2 C2 double dashed. We are honored by your presence. No, there was a lab, I remember.
We thought it is 545.
Okay, not a problem. C2 double dash. B1G. Then I plus sigma 3. S4 minus sigma 2 minus sigma 4. Sigma H plus sigma 1. Sigma V, yes, and 2 sigma D minus sigma 2 minus sigma 4. Add that all up, but now I don't have to, right? You can see. What do I get? I get sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. And Mayhock knows what the normalization constant is. So this is what we are discussing today, more about SLCs. I hope you have not forgotten what the projection operators are, right? So basically today what we will do is we will ensure that we get bored of projection operators. We will operate the projection operators so many times, okay? And the system that we are working on is PTCL for 2 minus, which is of D4H point group, okay? And the way we have drawn it is, this is your platinum, this sigma 1, sigma 2, sigma 3, sigma 4 are 4 s orbitals that chlorine atoms use for sigma bonding or dative bonding, whatever you might want to call it, right? This is the x direction, this is the y direction, z direction is pointing towards you and saying you are late, okay? So what we did is we used these 4 sigma orbitals and we constructed a reducible representation, and I am particularly proud about this nice straight line that I have drawn. So this is the reducible representation that we got, and while we were away we reduced this reducible representation into its constituent irreducible representation, and with a great difficulty we figured out that it is A1G plus B1G plus EU. So what we are trying to do now is we are trying to generate the A1G and B1G and EU SLCs, right? These are all sigma SLCs, okay? And we have already worked out 2 of these SLCs without your help. So you better help us work out the last one. One thing that should not be forgotten is that when you have a situation like this, two C4, 2C2 dash and so on and so forth, don't forget that they are actually different symmetry operations. It is just that they belong to the same class. So character is the same, but the effect will be different. So for example, 2C4 means one is C4 this way, the other is C4 that way, or you can think one is C4, the other is C4, C4 square, C4 cube, right. So see, if you start with sigma 1, the first C4 will take it to sigma 2, the second C4 will take it to sigma 4, okay. That is what we should not forget when we work out the projection operators. So are we ready for the last one, projection operator of EU? Huh? Shall we do it? And see, in this case even EU is easy because there are so many zeros. So you do not have to work with everything. I only have to work with E and C2 and I and sigma H, and that is it, isn't it? What was that? Okay, very good. Sigma 1 minus what? Okay, I heard sigma 2. So if you make the projection operator of EU operate on sigma 1, then you get sigma 1 minus sigma 3. What is the normalization constant? 1 by root 2. Okay, so we have generated 3 SALCs. How many SALCs should we generate? 4. And how do I generate the 4th SALC? Don't forget, the 4th SALC also has EU symmetry, which means that SALC along with sigma 1 minus sigma 3, wait, don't jump the gun, wait, it is not sigma 1 plus sigma 3. That along with sigma 1 minus sigma 3 is going to form a basis for the EU representation, because EU is a 2-dimensional representation, right? There are 2 1-dimensional representations, A1G and B1G. We have already worked out the SALCs for them. Now what is left is one of the SALCs for EU, because EU must have 2 SALCs. There must be 2 SALCs with EU symmetry, isn't it? So what you did, I think, correct me if I am wrong, is that you just worked out what is going to be orthogonal to this, isn't it? But see, there are several functions that can be orthogonal to this. You are looking for the specific function that will also belong to EU symmetry along with EU. So how do we do that? Now suppose I make the symmetry operations operate on this wave function sigma 1 minus sigma 3, this SALC. Then what will happen? What happens in a 2-dimensional basis when you apply the symmetry operations? Think of that x and y in C3V. What happened there? When I applied C3, x and y mixed, isn't it? Isn't it? X and y mixed. And when I applied sigma d, then what happened? In C3V, if you apply sigma d, then what happens? Then what happens? If I apply sigma d in C3V, I am talking about x and y in C3. See, I am talking about sigma v, not sigma d. What happens when I apply sigma v? X and y interchange, isn't it? X and y interchange. So this is what happens in multidimensional basis. Some symmetry operations cause a mixing of the basis elements, and some symmetry operations cause an interchange. An interchange, of course, if you think a little deeper, an interchange is really a very drastic case of mixing, isn't it? An interchange is just mixing in such a way that one of the coefficients has become 1 and the other coefficient has become 0. So, interchange is really a special case of mixing. So, essentially what happens in multidimensional basis, and this is a theme that we keep coming back to again and again, because it is very important to understand, is that in a multidimensional basis, a mixing of the basis elements takes place upon the symmetry operations. So, now see, if I now apply the symmetry operations on sigma 1 minus sigma 3, what should I get? I should get the other SALC of the same symmetry, or I should get a linear sum of sigma 1 minus sigma 3 and the other function, isn't it? Because once again think of x and y in C3V. When I apply C3, then what happens? There is a mixing of x and y. When I apply sigma v, then what happens? There is an interchange of x and y. When I apply E, then what happens? X remains x, y remains y. These are the only 3 things that can happen. So, if I go on applying the symmetry operations one by one, then I should be able to generate in some case the other SALC from this one.
You were talking about only a particular symmetry operation.
Yes, I will try out all. To start with, I am going to try out everything. What are the symmetry operations here? E, C4, then C2, etc., etc. To start with, we will try out all. And then later, we will think if we can make the problem a little simpler. Okay. So, let us try out all. What happens when E operates on sigma 1 minus sigma 3? I do not care about that 1 by root 2 at the moment. What do you get? You get the same thing. What is the next symmetry operation? C4. When C4 operates on sigma 1 minus sigma 3, what do you get? Sigma 2 minus sigma 4. And Rahul, are they orthonormal or not? Sigma 1 minus sigma 3 and sigma 2 minus sigma 4, are they orthonormal or not? So, this could be an SLC. Yes. It does not matter, it is just negative. It is just plus x and minus x. It is up to you. Okay. What is next after C4? C2. C2 operating on sigma 1 minus sigma 3, what will you get? Same thing, right? Sigma 3 minus sigma 1, which is minus sigma 1 minus sigma 3. See, it is unfolding in front of our eyes, isn't it? What is going to happen? Then what about, what is next? C2 dashed operating on sigma 1 minus sigma 3. What do we get? Sigma 2 minus sigma 4 once again. So, now the suspicion is getting stronger and stronger that sigma 2 minus sigma 4 seems to be the other wave function, other SLC rather. C2 double dash, C2 dash, huh? Which one is C2 dash? This. So, C2 dash should give me what? This is one C2 dash, that will give me sigma 1 minus sigma 3. What about this C2 dash? Sigma 1 minus sigma 3. So, and what about C2 double dash? Sigma 2 minus sigma 4. So, it is very convenient, add a dash. I am really getting on the nerves of some of us. And then C2 dash operating on sigma 1 minus sigma 3 gives us sigma 1 minus sigma 3. Okay, what is left? S4. What do we get? Sigma 2 minus sigma 4 or sigma 4 minus sigma 2? Depending on which direction you turn, right? But it does not matter, it is just plus minus. Sigma 2 minus sigma 4. Then I. Then sigma h, that is too simple. I will not insult your intelligence by asking you this. Sigma v, sigma v. Okay, you do not want your intelligence to be insulted, so I will write it. sigma d plus minus, right? Plus minus, fine. Sigma d, sigma 1 minus sigma 3 once again. Yeah. So then sigma 2 minus sigma 4 is the fourth, what is it called? SALC. And it is the second SALC which has the EU symmetry. Okay? Right? What is the property that has to be satisfied for it to have EU symmetry? You take sigma 1 minus sigma 3 and you take sigma 2 minus sigma 4. We just worked out all the symmetry operations. So what we see is that they either interchange or they remain what they were. That means they are jointly forming a basis of EU. They are not forming the basis for any one dimensional representation because they are interchanging between each other, right? So they jointly form the basis for this two dimensional representation. Okay, Dibyendu? Fine, that was very easy.